In mid-November 2025, a telescope in Rayong, Thailand, captured an image that should not exist. A single comet, an interstellar visitor known as Cosmiq Atlas, was seen displaying three distinct tails pointing in three different directions. One tail bent gracefully along the object's orbit. Another stretched directly away from the sun, shaped by solar wind. And the third, the one that has shaken astronomers, pointed back toward the sun, sharper and brighter than ever before, at a time when it should already have faded into nothing. This unlikely structure violates everything we know about comet physics. It defies the expectations of solar radiation, orbital mechanics, and hundreds of years of observation. And it appears precisely at a time when activity should be collapsing, 18 days after perihelion, the point where all comet tail structures normally weaken, broaden, and drift into chaotic dispersion. Yet here, an impossible anti-tail stands brighter and more coherent than it was weeks earlier. And the closer we look, the stranger the story becomes. Comets are frozen reservoirs of ancient material, drifting for millions or billions of years until their elliptical orbits bring them near the sun. When heated, their ices sublimate directly into gas, dragging dust into space and forming two predictable structures. The ion tail, created by charged gas stripped by solar wind, always pointing directly away from the sun. The dust tail, formed when sunlight pushes dust backwards in a curved arc that traces the comet's orbit. Both tails are well understood. Both follow stable rules, and both behave consistently across thousands of comets observed through centuries. But there is a third structure, one that appears only under rare conditions, the anti-tail. This feature is an illusion produced when Earth crosses the comet's orbital plane. Large, heavy dust particles lagging behind the nucleus form a thin disk, and when viewed edge-on, that disk seems to point toward the sun. Anti-tails form briefly. They fade quickly. They do not survive long past perihelion. But Cosmiq Atlas is not following the script. Late September, early October. As Cosmiq Atlas approached the sun, early images captured the expected anti-tail. It appeared exactly when geometry predicted and behaved as textbook models describe. This was normal. October 29, perihelion. The comet passed its closest point to the sun. Many expected a fragmentation event or structural breakup. None occurred. Instead, it emerged intact, with activity stronger than expected. Early November. The anti-tail remained visible. This was unusual but not alarming. Astronomers noted that the structure looked sharper than expected, but assumed it would begin fading shortly. November 10. The Virtual Telescope project in Italy imaged the comet and confirmed that all three tails were still present, ion, dust, and anti-tail, long after they should have begun collapsing. November 13-15. The turning point. A 0.26-meter telescope in Thailand imaged the comet under near-perfect sky conditions. The anti-tail was not fading, it was strengthening. Its boundaries were sharp, its structure coherent, its brightness comparable to or even exceeding that observed during perihelion. This is where the anomaly becomes undeniable. This is where normal explanations begin to fail. A true anti-tail, created by geometry, not by ejection, has two properties. Large dust grains disperse rapidly once solar heating decreases. Viewing geometry changes quickly, so the illusion stops forming. At 18 days past perihelion, anti-tails should be ghostly smudges requiring long exposures to detect it all. Instead, Atlas shows a structure almost blade-like in sharpness. To maintain such a beam, particles must either be extremely massive, resisting dispersion, be continually replenished even after activity should be dropping, or be somehow kept aligned and focused in a way no natural tail has been seen to do. This is the puzzle scientists cannot yet solve. Astronomers currently consider three leading natural mechanisms. Each explains some part of the mystery, but none explain all of it. If 3I Atlas released far more millimeter-scale particles than a normal comet, the antitail could persist longer simply because there are so many large grains. That dispersion takes more time. This explains the persistence, but not the sharpness. After 18 days, dispersion should blur the edges. Instead, images reveal a narrow column with crisp boundaries, something large particles cannot maintain without a focusing mechanism. If the nucleus shattered into several icy pieces, each fragment could act like a miniature comet, producing its own gas and dust stream. Multiple jets could combine into complex tail structures. But fragmentation produces chaos, not coherence. A fragmented nucleus typically yields irregular plumes, asymmetrical dust fans, and uneven brightness patterns. None of that is observed. The nucleus appears compact. The antitail appears smooth and organized. This theory struggles to fit the data. Some comets possess vents, cracks, or openings that emit highly focused gas jets. If 3I Atlas had a jet pointing in just the right direction, it could sustain a narrow beam-like structure. The problem is rotation. Comets spin. A jet tied to the surface should sweep like a lighthouse beam. But the Atlas antitail shows no sign of periodic sweeping, widening, or bending. To maintain a single direction for weeks would require an incredibly slow rotation or a vent located exactly at the rotational pole. Both are possible, but unlikely. Each theory answers part of the puzzle. Heavy dust explains longevity. Fragmentation explains complexity. Jets explain focus. But none explains sharp, coherent structure persisting for weeks during a period when comets universally fade. This is why 3I Atlas is now considered one of the most mysterious interstellar objects ever observed. There is another possibility, not exonic, but profound. 3I Atlas may be chemically unlike any comet we have ever studied. It formed around a different star, in a different nebula, in different temperatures, under different cosmic conditions. Early spectroscopy shows unusually high carbon monoxide levels, far higher than common in our solar system. Sea ice sublimates at far lower temperatures than water. This means activity begins earlier, activity lasts longer, gas velocities may differ, dust particles may behave differently. If Atlas contains exotic volatiles or unfamiliar organic compounds, its activity profile and dust dynamics could be unlike any comet born in our solar system. This alone could account for persistence, but again, not necessarily the precision of the antitail. The mystery now hinges on one critical measurement: the velocity of particles inside the antitail. Natural sublimation produces particle speeds typically under 1 kilometer per second. If the particles are moving far faster than that, natural gas pressure may not be the cause. Upcoming observations, especially spectroscopy during the December 19th closest approach, will reveal whether particles are accelerating unusually, whether gases in the antitail differ chemically, whether the structure shows rotation-linked variations, whether the antitail begins to break up or strengthens further. This data will determine which explanation survives. On December 19, 2025, Earth reaches the best observational geometry. Every major telescope, from ESO's Very Large Telescope to global amateur networks, will target 3I Atlas to collect high-resolution spectroscopy, multi-wavelength imaging time series, brightness tracking thermal emission signatures, particle motion measurements. This is the moment the mystery may crack open. If velocities match known comet physics, the anomaly remains strange but natural. If velocities exceed natural mechanisms, the discussion shifts to new territory, either poorly understood physics of interstellar ices or something far more unexpected. 3I Atlas is the third confirmed interstellar object ever observed. 1I Oumuamua, too strange to classify. 2I Borisov, the most normal. 3I Atlas, the most detailed and now the most unexplained. Each object behaves differently. Each challenges modeling. Each expands our understanding of cosmic wanderers. But 3I Atlas stands out because it is revealing its secrets in real time through continuous global observation. And its most startling feature, the anti-tail that should not exist, remains, for now, unanswered. 3I Atlas is forcing astronomers to confront an uncomfortable truth. Our knowledge of comet physics is based entirely on objects born in a single solar system, ours. But the galaxy is not uniform. Other star systems may produce materials and structures far beyond what we have cataloged. The persistence and sharpening of the anti-tail point towards something unusual happening, whether it is a massive particle cloud resisting dispersion, exotic ices maintaining activity, a stable jet oriented with improbable precision, or physics we do not yet understand. The next few weeks, and especially the December 19 observations, will determine how deep this mystery truly goes. Until then, 3I Atlas continues its silent glide through the inner solar system, carrying with it an impossible glowing spear of light pointed defiantly back at the star that should have erased it. A reminder that even now, even here, the universe is still capable of breaking its own rules.